Okay, so today I'll be discussing some questions regarding the week 4 syllabus. That is, we have reheater and also we have intercooler. Okay, so as you can see here, reheater is basically a device which is added downstream of the high pressure turbine, basically between a high pressure turbine and a low pressure turbine in a turbojet engine. And the purpose of using a reheater is to increase the temperature of the fluid after it has crossed the turbine, right? So you can see in the TS diagram that in the ideal situation, first the fluid, that is the air which is being taken in from the atmosphere, that undergoes compression, and that is in the compressor, and then it undergoes combustion along with fuel addition, so that happens in the combustor, and from 2 to 3 combustion is happening. 3 to 4 is a high pressure turbine. So in this turbine the flow will expand, and as you can see the temperature is going to decrease. And then after that, in a normal situation when there is not a reheater attached in the turbojet engine, we will simply expand this fluid through the nozzle, right? But then what we do is we have this reheater where we are adding heat to increase the temperature from this station 4 to station 5, and then we expand this fluid which is at a higher temperature now through a low pressure turbine. So basically we are dividing the work and we are trying to generate more work. So in the high pressure turbine, if we would have generated enough work and the temperature at station 4 was very low, then expanding it through a low pressure turbine will not generate enough amount of work. So what we do is we basically add this heat and then expand that a fuel air mixture through the low pressure turbine and generate heat. Okay, so this is the work of a reheat. And then the second important thing that is it is an intercooler, and intercooler is used between compressors. So for example, say we have these multi-stage compressors, compressor stage 1 and 2. So what we do is we add this intercooler in between. So what happens in a compressor, so when you're compressing the air, say for example you are just compressing the air from this state 1 to state 2. Okay, so let me draw this here. Yeah, so if you're basically compressing from this state 1 to state 2 prime directly, then you have increased the temperature and also you have increased the pressure. Now instead what we do by using an intercooler is we start from this state 1 and then we go to this state C, that is after the first compressor. Okay, so compressor 1 has done its job, it has increased the temperature and also the pressure, and then using this intercooler we basically lower down the temperature at constant pressure. So you can see that on this constant pressure line we are decreasing the temperature, and then from here the temperature will increase due to compression in the second stage of the compressor. So now what have we done? We have achieved the same pressure P2. So the pressure ratio across this multiple stage compressor is the same, which is P2 by P1, right? But if you compare the temperatures which have been reached, you can see that because of the intercooler we have been able to achieve a lower temperature. So T2 is less than T2 prime. Okay, so now here are two simple questions. Question 1 is, in a gas turbine plant, a regenerator increases which one of these? Work output, pressure ratio, thermal efficiency, or all of the above? So let's go back to the diagram of the regenerator. Now regenerator is not changing the work output, because if you would have not added the regenerator or reheater over here, basically you would have achieved the same amount of work. which you are achieving right now because of the high pressure turbine and low pressure turbine. What you are essentially doing by adding this reheater is increasing the thermal efficiency, because now in the low pressure turbine, because the fluid was at higher temperature, the expansion of higher temperature gas will help you increase the thermal efficiency. So the answer here is going to be thermal efficiency, right? Okay, question 2, in a gas turbine, what is the function of a reheater? It is basically to heat the gas coming out of the high pressure turbine. Okay. Alright, so now we have some numerical questions. A gas turbine power plant operates at a pressure ratio of 6.5 with intercooler and reheater placed at their optimum conditions. So what are the optimum conditions? Like we showed in the previous diagram, intercooler is between two compressors, a reheater is after the high pressure turbine. Okay, so now what is given to us are the inlet conditions. So I'll just note down the inlet conditions over here. T1, which is the inlet condition, is given to be 290 Kelvin. P1, the inlet pressure, is given to be 1 bar. Alright, the maximum temperature of the cycle is limited to 1020 Kelvin. So if I just draw the cycle over here, as you can see, this is the temperature, and the x-axis is the entropy. So in the TS diagram, we start from this state 1, which is the inlet, and then we have a low pressure compressor, and after that there is a high pressure compressor. Between these two we have the intercooler. That is why you can see this decrease in the temperature. So between the low pressure compressor and high pressure compressor, because there is an intercooler, the temperature is decreasing at a constant pressure line. And then after the high pressure compressor, there is combustion. So we are basically adding some fuel, and there is heat added to the fluid in the combustion chamber, and then you achieve the state 5. And from state 5, you allow the fuel air mixture, which is the fluid, to expand in the high pressure turbine, and then you achieve the state 6, after which you have the reheater. And the reheater will basically increase your temperature at constant pressure. So again, 6 to 7 is a constant pressure line, and you're adding heat over here, so we are going to achieve higher temperatures. And remember that in an ideal situation, what is going to happen is that T5 is equal to T7, and that is equal to the maximum achievable temperature, which is given to us as 1020 Kelvin. Okay, and then finally 7 to 8 is your low pressure turbine and nozzle. That is the entire cycle. Okay, so now what we have been asked is the actual temperature at the exit of the high pressure compressor, the actual temperature at the exit of the low pressure turbine. So okay, what is the exit temperature after the high pressure compressor? So you come back to the diagram, you have the low pressure and then the high pressure compressor. So the exit temperature is 4, station 4. So I'll write here, we need to find T4. And question 4, we need to find basically the temperature at the exit of the low pressure turbine, which is T8. So we've been asked T8. And then the total or the summation of the heat added into the combustion chamber and the reheater. So we need to find QCC plus QRH. Alright. And then we need to find the work ratio of the cycle and the efficiency of the cycle. So let's get to work. We have to solve the entire cycle, and we are also given the efficiency of the compressor and the turbine, which is eta C is equal to eta T, and that is equal to 0.85. Okay, and then we are given this Cp and gamma for the fluid. Okay, so let's start with what happens in stage 1 to 2. assuming in ideal situation, we can use the isentropic relations or adiabatic relations. That is, we know that P2 by P1 is equal to T2 by T1 to the power gamma by gamma minus 1. Okay, and how do we find P2? So remember, we were given also the pressure ratio Rp as 6.5, right? And in an ideal situation, despite using the intercooler, the pressure ratios should remain same, right? And both the high pressure and low pressure compressor have the same pressure ratio. So now we can simply find P2 is P1 times Rp. And okay, I'm sorry, it's under root Rp. So that turns out to be 2.5495 bar. Okay, and then for the low pressure compressor, we have this relation from which we can basically find T2. But remember, this is going to be my T2 prime, which is the isentropic path. Okay, so T2 prime using this particular relation turns out to be 378.67 Kelvin. Okay, now we can use the efficiency of the compressor, which is given to us as 0.85. And remember the definition of efficiency, we have discussed this earlier. It is T2 prime minus T1 divided by T2 minus T1. And using this relation, see, we have the value of T2 prime, we have the value of T1. So we can find the value of T2, which is the actual temperature at the exit of the low pressure compressor, and this turns out to be 395 Kelvin. Okay, so if you go back, what was asked was the exit temperature at high pressure compressor. So we have solved for only the low pressure compressor. So now we will do it for the high pressure compressor. But if I go back to your intercooler diagram, you can see that despite using the intercooler, I should have achieved this temperature which is lower than what you would achieve in the direct path, right? So if you come down, due to perfect intercooling, so I'll write here, due to perfect intercooling, T2 is going to be equal to T4, and hence we have the exit temperature at the exit of the high pressure compressor, which is 395 Kelvin. Okay, so now the next task is to solve for the combustion chamber, and also we need to solve for the turbine. So we know that the work for a compressor comes from the work that is done by the turbine, right? So what is the work for compressor? We have in the ideal situation, work done by low pressure compressor is equal to work done by the high pressure compressor. So this is equal to Cp T2 minus T1. Okay, and this because we have found T2 now, we can write, we can find the answer, that is 104.8 kilojoule per kg. Okay, and what is the heat input in the combustion chamber? So I'll write what is the heat input for combustion chamber as Cc. That is equal to Cp into T5 minus T4. So go back to the diagram. You can see that combustion chamber is in this station, right, between 5 and 4. So okay, so Cp into T5 minus T4. So for this, we need to find T5. But T5 is given to us again, that is 1020 Kelvin, which is the maximum possible temperature, and T4 we found just now, which is 395 Kelvin. So okay, so this is given 1020 Kelvin, and T4 is also known. So now you can find the heat input to the in the combustion chamber, and that turns out to be, I'll just plug in the values. This turns out to be 628.83 kilojoule per kg. Okay, right. So the next stage in the turbojet engine is the turbine. So for turbine, again we'll apply the isentropic relations, that is T5 by T6 prime. So this is the ideal state 6 prime, that has a relation to the pressure ratio P5 by P6 prime whole to the power of gamma minus 1 by gamma, right? Okay, now if you want to refer the figure, the pressure for at the state 6 prime and at state 6 is going to be same. Okay, so I'll just make that note here, that P6 prime is anyways equal to P6. Okay, so now given T5, we need to find T6 prime, and P5 by P6 we found earlier, that was equal to 2.5495, right? In this to the power 0.4 by 1.4 multiplied to the value T6 prime, that gives me T5, but T5 we know from the question is 1020, so now we can find T6 prime, right? So T6 prime is basically equal to 781.19 Kelvin. Okay, so how did we get this value P5 by P6 prime? In an ideal case, the pressure ratio across the high pressure turbine will be the same as one stage of the compressor, and that is what we got here from the root of Rp, right? And in case you're wondering why there is an under root, so remember the total pressure ratio of the compressor was given, that was P4 by P1, but that is equal to what? P4 by P3, and that multiplied to P2 by P1, right? And because both of them have the same value, so let me say this was basically P2 by P1 whole square, right? Because we are saying that the pressure rise in the low pressure compressor is equal to the pressure rise in the high pressure compressor. So that's why, because this is defined as Rp, we got P2 by P1 as equal to under root Rp. Okay, so that's what we had used here, and the same pressure ratio will be across each of the turbines, the high pressure and the low pressure turbines. Okay, so going back, we plugged in the value of the pressure ratio here. The pressure at station 5 is obviously higher than 6. Okay, so T6 prime we have obtained as the ideal exit temperature of the turbine, but we need to find the actual exit temperature, and that we can find because we know the efficiency of the turbine, which was given to us as 0.85. So if I just plug in the equation, which is, so we remember how to define this temperature, right? T5 minus T6 divided by T5 minus T6 prime. Okay, so this basically gives us that T6 is equal to 817 Kelvin. So that is one of our answers. Right. So we have found the temperature at the exit of high pressure compressor. We found the temperature at exit of the low pressure turbine. Okay, again, we were supposed to find T8. We have only found T6 right now. But as you can see, in the ideal situation, these two temperatures T4 and T2 are supposed to be same, and T6 and T8 are supposed to be same. So with an ideal intercooler and an ideal reheater, uh, these are the situations. So since we are not given any efficiencies or any such definitions for the intercooler, we are assuming them to be ideal, and that's why we have basically, so this is an important point, so I'll just maybe make a note in the diagram. T2 prime is equal to T4 prime, and automatically, because the pressure ratios and efficiencies are same across both the compressors, we get that T2 is equal to T4. Alright, and similarly you can see that T6 prime is equal to T8 prime because the reheater is ideal, and then automatically you get that T6 is equal to T8 because again the efficiencies for both the high pressure and the low pressure turbine are same. Okay. Okay, so then the next thing we need to find is basically the work ratio and the efficiency, right? So how do we find the work ratio? Work ratio was defined as the WR work ratio is defined as the net work in the cycle divided by the work done by the turbine. Okay, so to find the net work, we need to find the work done by the turbine minus the work done by the compressor, and that divided by work done by the turbine. Okay, so work done by compressor we have already found for low pressure and high pressure compressor, so we need to find the work done by each of the turbines. So yeah, work done by the high pressure turbine plus the work done by the low pressure turbine is basically equal to the total work of the entire cycle, total work done by the turbine, right? And this we can find as Cp into T5 minus T6 plus Cp into T7 minus T8. Alright, so now we know all these values, all the temperature values, and Cp is given to us. So you can plug in the value and get the total work of the both the turbines. That gives you 408.03 kilojoules per kilograms. Alright, then the net work will, you can find out, is nothing but the work done by the turbines in total. So I'll write total turbine minus work done by the both the compressors, so total work done by the compressors, and this is basically equal to 408 minus 2 times of 104.82, because going back, if you remember, the work done by both the compressors was equal, and we found work by each of the compressors to be 104.8. So here we are going to multiply by this 2. Alright, and that gives us the value of the net work done as 198.39 kilojoules per kg. So then we can find the work ratio. So work ratio is equal to 0.49. And the next task was to find the heat. Okay, we had to also find the heat that is added in the combustion chamber and the reheater, and the total efficiency of the cycle. Okay, so I'll just add a page here. Okay, so now we already found the value of the heat added in the combustion chamber, and that was basically the value was 628.83. Okay, so I'll rewrite it here, 628.83 kilojoules per kg. Okay, now we need to find how much heat is being added between station 7 and station 6, that is the due to the reheater. So that we can find as Q in the reheater is equal to Cp T7 minus T6. Again, we have all these values. T7 is the maximum achievable temperature and T6 we have found earlier as 817 Kelvin. So what is the heat in the added in the reheater? It is equal to 204.02 kilojoule per kg. So now we can define the efficiency. Efficiency is the work, the net work produced by total heat input into the cycle. Now remember, because we have a reheater, we also have to include the heat of this reheater. So in an ideal turbojet, we only take the heat from the combustion chamber, but now we will also include this from the reheater, and we have already found the net work to be 198.39, and if you add up the total heat, it will be around 833. Okay, and both of them have the same units. The net work was also in kilojoules, so okay, that is fine. So you find that the efficiency is about 0.24. So efficiency is like 24%. Okay. So now I'll move on to the next question, which is also a numerical. Now in this case, we are dealing with an open cycle constant pressure gas turbine plant, and the air enters at 1 bar and 310 Kelvin. So I'll start writing the input parameters, that is T1 is 310 Kelvin, P1 is 1 bar. The cycle consists of two-stage compression with perfect intercooling. So again, we remember what happens in perfect intercooling. You have this, these two temperatures are going to be same, right? So T2 prime is equal to T4 prime, and T2 is equal to T4. Alright. Let me just make the axis over here. So this is the T axis, and we have the S axis, entropy. Okay. So the cycle consists of these two-stage compression with perfect intercooling and a single-stage turbine with exhaust heat exchanger. So the cycle is limited to a maximum pressure ratio of, so Rp is given to us, is equal to 7, and a maximum temperature, so T max is equal to 1023 Kelvin. Okay. The isentropic efficiency of compressor and turbine is given, so eta C equals eta T is equal to 0.88. Now you have to consider the effectiveness of the heat exchanger to be 95%. So I'll denote that by epsilon. Epsilon of the heat exchanger is given to be 0.95. And for the maximum expansion work, we have to find the temperature at the exit of the high pressure compressor, which is nothing but T4. Okay, the total heat input in both the compressors, okay, so that we have to find is QHE, and then the net work output of the plant, work ratio, and the thermal efficiency. Okay, so let's get started. Now in the case of a heat exchanger, what are we doing? We are basically we place this heat exchanger between the compressor and the combustion chamber. So using this heat exchanger, we are increasing the temperature of the fluid before it is inlet into the combustion chamber. Okay, so in a simple Brayton cycle, first you have the compression and then directly you have the combustion. But now what we are doing is we are basically letting this fluid exchange heat with some other fluid. And where does that some other fluid come from? It comes from the turbine. So in the compressor, first the fluid undergoes compression, Then in the turbine, it undergoes expansion. The flow is still hot, and that hot flow is extracted, and it is brought into contact with this flow which is coming out of the compressor. Okay, so if I just remake this diagram in a more simple manner, so say you have this TS diagram, right? This is your T axis and this is your S axis. So what we do is, say we were at this stage 3 and then there is a compression. So this compressed gas at stage 4 has a certain temperature T4. Now the aim is basically we need to raise the temperature, but we don't want to use a lot of fuel, right? So if I can raise the temperature up to some point, say T5, without even using the fuel, that's well and good. Then I will have to use lesser fuel and achieve this temperature T6. If I didn't have the heat exchanger over here, then I have to achieve the difference T6 to T4, this entire difference, by using fuel. But now because I have this heat exchanger, I will have to use lesser fuel, right? And from T6 to T7, we basically allow expansion. Now you can see that this flow is at a much higher temperature. So what we do is we allow it to cool slightly at almost constant pressure, and this gives me T8 such that it is almost equal to T4. Now what are we doing here? So the entire heat which is lost by this fluid, that is from T7 to T8, some heat is going to be lost by this hot fluid coming out of the turbine, and that is going to be equal to the heat gained by the fluid at the exit of the compressor. Okay, so this is T5 minus T4. So this is the ideal situation of a heat exchanger. Now what happens in the case where the heat exchanger is not very efficient? Then we can define an efficiency of the heat exchanger, which would be what is the actual heat transfer by the maximum possible heat transfer, right? So what is the maximum heat transfer equal to? Maximum heat transfer is going to be from T7 to T4, because see, you start with a hot fluid which was initially at a temperature of T7, so that is T7, and you're going to achieve T8, but in an ideal situation T8 is equal to T4, so I'm going to write T7 minus T4, and in the numerator we have the actual heat transfer. So what is the actual heat transfer going to do? It is going to increase the temperature from 4 to 5. So the actual heat transfer was actually T5 minus T4. So this is the definition of the efficiency of a heat exchanger. Yeah, so like I said, ideally we have T8 equal to T4, and of course we want T7 to be equal to T5. But in reality we will not be able to achieve this. T5 will be lesser than T7, and to find that, we have been given this efficiency of 0.95 for the heat exchanger. Okay, so let us now solve the cycle and get all the values. So across the low pressure compressor, again, what is the pressure ratio? So like I explained in the previous question, P2 by P1 is under root of the total pressure ratio across both low pressure compressor and the high pressure compressor, right? So this is going to be under root 7, and we have also been given P1 as 1 bar, so this gives me P2 is equal to again 2.6457 bar. Alright, then we use the adiabatic relations, assuming an ideal condition at 2 prime. So T2 prime by T1 will be equal to P2 by P1 whole to the power of gamma minus 1 by gamma. Okay, so that gives me T2 prime. And then I also have the value of the efficiency of the compressor, the definition of which is T2 prime minus T1 by T2 minus T1. Okay, so that will help me get the value of T2. Alright, so T2 prime turns out to be 422.8 Kelvin, and because the eta C was given, remember it was 0.88, so this gives me T2 of 423 Kelvin, and again T2 is equal to T4 for ideal intercooler, because nowhere has the question said that the intercooler is not ideal, so we'll simply assume it is ideal. Okay, so we got T2 is equal to T4. Alright, so then we can find the work done by the compressor, which is going to be the work by the low pressure compressor plus the work by the high pressure compressor, and that is equal to 2 times the work by the low pressure compressor. So that is 2 times Cp into T2 minus T2. Okay, so now this is this you can find is 227 kilojoule per kg. Okay, then the next part is solving for turbine. So let me maybe change the color over here. So for turbine, we have the inlet temperature, right? Because we have the maximum possible temperature, that is T6, that is given to us. The maximum temperature is 1023 Kelvin. So I'll write T6 is equal to 1023 Kelvin here. Now note that we don't have any reheater or anything, so there's simply from 6 to 7 there is a turbine. Okay, so for turbine again we can apply this isentropic condition that T6 by T7 prime is equal to P6 by P7 whole to the power gamma minus 1 by gamma. And now since we don't have 2 stages, the total drop of pressure in the turbine is going to be the maximum whatever is given in the question. So the question says that the maximum pressure ratio for the entire cycle is defined as 7. So for even for the turbine it is going to be 7, and here we will say 7 to the power 0.4 by 1.4, and remember T6 is known to us, so we can get T7 prime. T7 prime turns out to be 587.53 kelvins. Alright, and again we have the efficiency of the turbine, which is nothing but T6 minus T7 divided by T6 minus T7 prime. So this turns out to be this is given to be 0.88, so then T7 turns out to be 639.78 Kelvin. Okay, so now we can find the work of the turbine. Work done by the turbine is Cp into T6 minus T7. Remember we just have one turbine in this case, so this is equal to 385.136 kilojoule per kg. Okay. Okay, so now it's just simple calculation. The net work is equal to work done by turbine minus work taken by compressor, and this is equal to 159 kilojoule per kg, and the work ratio can also be found. So work ratio is equal to the net work by the work done by the turbine, and this is equal to 0.4. Okay, now since we have been given this efficiency of the heat exchanger, and the definition over here is like we discussed just now, T5 minus T4, which is the actual heat transfer by the maximum possible heat transfer, which is T7 minus T4, and this we know is 0.95. So we have the value of T7. We just found it over here, okay, from the turbine. And then we also have the value of T4, which we found from the compressor. Okay, so the only thing we don't know is T5. So we can find T5 using this definition and the given value of the efficiency of the heat exchanger. And T5 turns out to be 628.93 Kelvin. Okay, and then finally we can find what is the heat input in the combustion chamber, because remember, if we didn't have the heat exchanger, we could have simply got the value as Cp times T6 minus T4, because you will have to add the fuel to raise the temperature from the exit temperature of the compressor to the inlet temperature of the turbine. So all that work will be done by adding fuel. But now, because you have the heat exchanger, you have to basically add lesser amount of fuel, and that's why the amount of heat that you are going to add in the combustion chamber is going to be smaller, and that can be found as Cp into T6 minus T5, right? So this turns out to be 396.039, yeah, kilojoule per Kelvin, kg. Okay, so you can just approximate this to 0.04. Okay, so now we can find the efficiency of the entire cycle, which is nothing but the net work of the cycle divided by the total heat input, and that turns out to be point, oh, 0.399 or approximately 0.4. So the efficiency is like 40%. So that's all for the tutorial for week 4. Thank you.